Welcome back, sports fans. Today we're going to talk about centripetal force. We're going to try to give you the basics of what you have to know here. Today you're going to learn about centripetal acceleration, how the centripetal acceleration combines with mass to find the centripetal force, and why objects travel in circular paths. A centripetal force is a force that causes an object to accelerate to the center of the circle. Example, ball on string, satellites in space. So, again, what we're talking about here is some type of force that causes an object to be accelerated towards the center. Alright, and that is your centripetal force. The string is constantly supplying a force that is perpendicular to the speed of the ball. If the string were to break, the ball would travel off in a tangential course. So if the string were to break, this ball would take off in that direction. It would be traveling at a tangential. So what causes anything to travel in a circle? Well, it is this centripetal force. Some of you might be saying, well, the string is the force of tension. Well, that is true. In this case, this force of tension is supplying that force that's pulling it to the middle. So besides the fact that it is a force of tension, it's also supplying a centripetal force. There's lots of things that could give a centripetal force. For anything to travel in a circle, there has to be some type of centripetal force acting on it. In this case, it's the string right here. It's this tension in the string which is causing it to travel in a circle. Imagine holding on to the edge of a merry-go-round as a young child. It was hard to stay on the merry-go-round. Where did you sit if you didn't want to fall off? Well, the closer you sat to the middle, the easier it was to stay on because you weren't traveling as fast. Let's go on to the next one here. Centripetal acceleration. Key concepts. Alright. What we're looking at here is our equation down here. The centripetal acceleration. So we're going from centripetal force to centripetal acceleration. I don't know, maybe I should have talked about these in the opposite order, but the centripetal acceleration can be calculated by the square of the velocity over the radius. So what does that mean? Well, as the radius decreases, the centripetal force increases. Why? Because the acceleration is going to get bigger as the radius gets smaller. So, and basically if we divide by smaller numbers, the answer gets bigger. So if I divide by 10, I'm going to get one answer, but if I divide by 1, I'm going to get a larger answer, which means the acceleration gets bigger, which means the force gets bigger. And well, your mass is not going to increase, you're just getting closer to the center. So how then? Well, the centripetal acceleration increases, as we just discussed. Well, let's talk then. We've talked about what centripetal force was. We talked about how to calculate centripetal acceleration. Let's talk about how to calculate centripetal force now. This is a force that causes an object to accelerate to the center of the circle. In this case now, we've gone in here and we've replaced the A with V squared over R. So instead of having F equals MA, because A equals V squared over R, we've taken that and put it in for A. And that's what gave us then that equation. So our example, the ball at the end of a string is 200 grams. The ball is moving at 5 meters per second. The string is 75 centimeters long. How great is the tension in the string? Well, the force of tension is our centripetal force. So I'm going to go back to our sum of forces equation here. In this case, it's a centripetal force. And what's supplying the centripetal force? Well, the only thing that's supplying it is our tension. So if I say mv squared over r is equal to the force of tension, it's just a matter of plugging in what we know here. The mass is 200 grams, which is 0.2 kilograms. The velocity is 5 meters per second squared, or 5 meters per second, and we're going to square that. And the radius is 75 centimeters. Well, in meters, that is 0.75. That gives us a centripetal force that is equal to 6.7 newtons. Alright, some more examples. 1,500 kilogram car is traveling at a rate of 27 meters per second. It takes a turn that has a radius of 100 newtons. What is the centripetal force? Well, let's draw a picture here. I've got this car that's taking this turn, has a radius of 100 meters. And it's going at a velocity 27 meters per second. Well, first of all, what's supplying the centripetal force? In this case, it is friction. Alright, the friction between the tires and the road. There is no string attached to the car. So what else is holding it in place? It's the force of friction. If there were no friction on the road, you wouldn't be able to make the turn. If there was no friction between the road and the tires, you wouldn't be able to make that turn. So in my sum of forces equation, it's an easy one. The sum of the forces which is supplying the centripetal force is the force of friction. Well, again, mv squared over r is equal to that centripetal force. So our mass is a 1,500 kilogram car. The velocity is 27, and our radius is 100 meters. Our centripetal force then is 10,935 newtons. Now, this equation that we're going to use here isn't perfect. We're going to actually go into more detail here in a few days to give you a better idea of how this works. But I'm going to start off by basically telling you that the reason we have anything in orbit, whether it's a moon or a satellite, is because there's a centripetal force acting on this satellite. Otherwise, it wouldn't be traveling. All right, so there's some type of, wouldn't be traveling in a circle. So there's some type of centripetal force. In this case, what pulls all objects to the center of a planet? Gravity. Now, gravity is actually going to change, but you'll get an idea good enough here, so it works for our example now. Again, we're going to go into much more detail later, but in general, the sum of the forces are equal to the weight of this object. And where I'm going to be wrong here is actually if it was that far away, gravity wouldn't be 9.8, but for right now we're going to go ahead and use it. So mv squared over r is equal to its weight, which is mg. So in this case, I'm going to start plugging in what I know. It's a 10 kilogram satellite. They want to know how fast does it have to go to stay in orbit. It's 1,000 kilometers, which is 100,000 meters. Don't forget to change that to meters. That's a mistake a lot of students make. Equals the mass again is 10 and gravity is 9.8. When we do that, I'm going to do some simple math here. Our 10s cancel each other out. If I multiply by 100,000, we get v squared equals 980,000. Square root both sides. You can get a velocity approximately of 990 meters per second. Now, the process here is correct of what we're doing here. I'm just trying to get you to understand that gravity supplies this centripetal force here. So we've talked about several things supplying that centripetal force. That can be friction between the road and the tires. The centripetal force can also be tension in a string, or the centripetal force, and I'm going to use a little different subscript here, which we're going to talk about here in a few days, is the force of gravity between two objects. It's going to be similar to what we just did here, but it's slightly different. Without having to go into much detail, I just wanted to introduce the concept that gravity also supplies a centripetal force. Well, hey, I hope that was beneficial. I'll catch you on the flip side.